Welcome to the presentation of Average Reward Adjusted Discounted Reinforcement Learning. I'm Manuel Schneckenreither and this is joint work with Georg Moser. As we all know, reinforcement learning is a machine learning method with astonishing results. It was used to solve chess, Go or Atari games. We are concerned with reinforcement learning in the context of operations research, and operations research is concerned with problem solving and decision making in the context of organizations and especially manufacturing environments. The overarching goal of businesses is the increase of value, and one key factor in that is the maximization of profit, or translated into our context, the most intuitive reward function is to choose decisions that return the highest expected long-term profit at every single decision point. Note that this reward function is fundamentally different to the spousal reward signals that we are usually used to, so the game-like domains as we have seen before. Discounted reinforcement learning in operations research has not received much attention until now. There are a few papers available which usually use sophisticated reinforcement learning methods, but then only handle very small problem sizes or report far from optimal solutions. So it seems that it does not scale very well in this context. A different approach was taken by Mahadevan, who in a series of papers investigated average reward reinforcement learning. In average reward reinforcement learning, no discount factor is used, but rather nested constraint problems are solved iteratively. These nested constraint problems are interconnected, meaning that if there is an estimation error in one level, this obviously has bad effects for the consecutive levels, constraint levels, or in other words, obviously this leads to very computationally intensive learning or long learning times, which more or less means that this is no remedy. So let's have a look at discounted state value, where we write the policy pi with an index of the discount factor gamma to indicate that the best policy is defined or dependent on the discount factor that we set. And as we all know, the discounted state value for a state S under discount factor gamma and for a given policy pi is defined as the sum of the discounted future rewards, where we write gamma for the discount factor and RT, or with the current policy pi of the state S, as the reward received at time t when following policy pi and starting in state S. And here in black are the important parts, whereas in gray are the not that important parts on which we don't want to concentrate, so that we can look at the important parts in the presentation. So what we did is we found four major issues when there is when the average reward per step cannot be approximated with zero with discounted reinforcement learning. And the first is that it may not infer optimal policies because the discount factor is strictly less than 1. To explain, let's have a look at this problem here, where we have one action choice of going left or right. If you go left, we do the printer loop, or the agent does the printer loop, which means it does 5 steps, and in the last step it receives a reward of 5. Or in other words, the average reward per step is 1 for the printer loop. If it does the mail loop, that means going right, it has to do 10 steps, but then in the last step receives a reward of 20. Whereas obviously the average reward per step here is 2, so the mail loop is preferred over the printer loop. However, if we set a discount factor that is 0.8 or smaller, the printer loop is preferred in discounted reinforcement learning. Then it is very difficult to specify a balance between short and long-term rewards in this setting. This leads to issues with the hyperparameterization, which we probably all had already had to deal with. Then, third, in case of terminal states, the average reward is simply ignored because there are no future states. Or in other words, for episodic MDPs, it doesn't work very well. And finally, in the case of unichain or ergodic Markov decision processes, the learning time is exponentially increased because although the average reward per step is shared among all the states, it's the same for all the states, the average reward is assessed independently for each state. So how we overcome this is with average reward adjusted discounted reinforcement learning. First of all, let's define the average reward. It is defined as, well, how we would define the average reward, meaning the sum of the rewards received of all the future steps divided by the number of steps taken. For unichain Markov decision processes, this average reward is equal among all states, as already said. This makes sense because if there is only one set of recurrent states, then we always end up in this set, and under the limit this obviously leads to the same average reward for all states. Thus, in the sequel we refer to it as rho under the policy pi, where we drop the dependency on the state. Then we can define the bias value. The bias value is the sum of the returned reward minus the average reward. So if we look at this, we can see that this value is bounded because we subtract the average reward. This value describes the reward that additionally sums up when we start in this specific state S. And finally, this leads us to the Leroy series expansion of the discounted state values, so of the state values that we are usually concerned with, which is already known since 69, which is the average reward divided by 1 minus the discount factor plus the bias value plus an additional term E, which is usually referred to as the error term and actually consists of infinitely many values, as this is the Leroy series expansion. And it is known that this final value, the error term, only exists because the discount factor is strictly less than 1. The idea of the error term is that it incorporates the amount and time until the value, until the reward, and especially until the bias value is collected. What we can see here is we have an exponential upscaling of the average reward, and usually in the environments that we use, the game-like environments, this average reward is more or less 0 because we have thousands of steps until we reach the end of the game and then have a reward of 1 for winning, -1 for losing, and hence this term usually equals to 0, and we only estimate these two terms. In operations research this is not the case, and this is the reason why it's not working very well. So with this we can already define the average reward adjusted discounted state values x of a state S under the policy pi, and note that we allow to set a discount factor of 1. This value x is given by the sum of the bias value and the error term, and the reformulation shows that this actually describes the discounted state value adjusted by the average reward. It's important to note that the Bellman equations of the standard discounted reinforcement learning framework adapt accordingly, which directly means that we can provide or develop an algorithm. As usual, we initialize the parameters and then loop until some stopping criterion is fulfilled. First, we choose with some probability a random action or otherwise the optimal one, then carry out this action, observe the reward and get the new state, just as in Q-learning for instance. Then an additional step that we have here in this algorithm is that if we have chosen an optimal, a non-random action, then the average reward is learned, whereas we use the returned reward, the current feedback, plus the best value of the future state minus the current state value. Note that we have a learning rate alpha here and use exponential smoothing to learn this value, just as in Q-learning again. Then in 6 we update the state values where we again have exponential smoothing and the same formula or almost the same formula as in Q-learning, so the reward plus the discount factor of times the best value of the future state, but additionally we subtract the average reward, and then we go to the next step. And we applied this algorithm to an admission control queuing system where we use a MM1 queue, which means Markov distribution or exponential inter-arrival time distribution, exponential processing times, and there is only one queue. The state space is given by a tuple of first the queue length L and then a Boolean variable where true T or true means that we have an incoming order where we need to decide on acceptance or rejection of this order. There are two errors for acceptance because either the currently processed order is not finished and the queue is the number of orders in the queue is increased, or at the same time or in the next step, until the next step, the processing is finished and although we accept, we directly produce the next order, meaning the queue does not increase, the queue size does not increase. Then we have the reward function given here, where we see that once we accept an order we receive a reward of 12, but in every step we have to pay a cost, where the cost function is f of the queue length, and this cost function is defined as C times L, with C equals 1. So the queue length defines how much we have to pay in each step. And these two values, the two rates that we have, arrival rate lambda and service rate mu, are both 5. And we have them here in the reward function, as this is an artifact from the transition from a continuous problem to an periodic MDP problem. There is a known optimal policy, which is to admit 3 jobs. As we can see in the results, our algorithm performs very well, where the optimum would be 3 million, whereas Q-learning does not perform very well, which is the first takeaway. Q-learning simply doesn't work in this context. And the second takeaway here is that we can set the discount factor to 1 as noted before, which is not allowed in Q-learning, and setting a lower value for the discount factor is no remedy in Q-learning, as you can see here. The learned average rewards, where 30 would be optimal, are almost optimal. Finally, in terms of conclusion and future work, we focus on problems that produce an average reward that cannot be approximated with 0, and presented a novel algorithm for unichain and thus also ergodic MDPs. We also provided ample evidence, and in the future we want to use neural networks for function approximation. There we actually recently published a paper as a first step, and then we also want to develop an actor-critic version. Thank you very much for your attention. We are available for discussion on Monday and Tuesday at these times, and please do not hesitate to contact us via email. Thank you very much.